Welcome to the course Business Analytics and Data Mining Modeling using R. So in previous few lectures we have been discussing different aspects of logistic regression. So we will continue that discussion in this particular lecture as well. So in previous lecture we used applied details dataset and then promotional offers dataset as well. Some of the details regarding modeling exercise we could not cover, so we will do that and discuss. So let's move to let's import this data set. So we'll let's import the library x+x. So we are again going to use this particular data set, write details. So let's import this. Now let's remove any columns, any rows. Let's look at these are the observations. Let's the structure for the data frame. So we'll follow some of the steps that we have gone through in previous lectures as well. So we'll just go through them. Now there is this particular exercise. In the previous lecture we had used a separate grouping for departure time. So again I have done certain changes into this grouping also, but this is not very important. However, let's run the model with a new grouping for departure time interval. So this is the range we already familiar with. So break is now 0 and 12. So these are the two breaks, 0 hours and 12 hours. And now this is how we are creating department variable. So if less than breaks 2 and breaks 1, then 0 to 12. So that means within, if the timing is within these two hours, 0 hours and 12 hours, then first category, that is 0 to 12. Otherwise it is going to be the second category, that is 12 to 14. So let's create this variable. Let's append this to the data frame. Let's change it to a factor variable, day variable as well. Let's cut the labels, change the labels, flight time. Let's also change it to appropriate format. Now this is the structure that we have now. Now after taking backup, we would not like to take forward some of the variables. So let's get rid of them. Let's look at this structure again. Now these are the variables. Now these are first few values, first 6 values. You can see everything is okay. Now let's work on the outcome variable like we have been doing in previous lectures. So let's change it to numeric code. Let's change the reference category. Now this is what it becomes. Now this is okay. Now we can move ahead. Let's do our partitioning. 2 partitions, training partition, testing partition, 90% for training partition and 10% of observation for test partition. Now the same function GLM that can be used to again model this. So these are the results. Let's look at once again. Now you would see every time, like we have been running this particular model on the same data set, and every time the significance levels have been changing, that as I have been explaining, smaller data set and therefore subject to change in terms of as the observation that are part of training data set, training partition, this results will also slightly change, and mainly with respect to significance level. Now we can see again flight carrier indigo has become significant 2-star level, right, and we can also see that destination has also become significant, right, and then we can also see flight time has also more high level of significance. However, more important thing is to look at the p values. We can see that this one source for Madras as well, this is also smaller p values. This is anyway significant flight carrier, and destination anyway this is significant at 90%. This is also significant. However, the new grouping that we have created out of departure time intervals, that also not comes out to be significant. However, p value is now smaller. So with this we will discuss the important aspect of logistic regression, So that is the measures of goodness of fit. So just like the linear regression, multiple linear regression, logistic regression also is a statistical technique primarily, and therefore in statistical modeling the main objective is to fit to data, as we have talked about this aspect many times before. So therefore in multiple linear regression we have a particular metric called multiple R square and adjusted R square, which are used to assess how good the model is fitting to the data. So similarly, since logistic regression is also a statistical technique, so there also we are required to have metrics for to measure the goodness of fit, how well model is fitting to the data. So what are those metrics? So because there is certain key differences in logistic regression and linear regression, so we'll talk about some of those metrics now. So you can see in the code that I have created a vector here, GF. First one is mod 3, the model that we have just computed, and we can see residual degree of freedom. So this df dot residual is the one of the value that is returned by the GLM function, and gives us the residual degree of freedom. Then we have deviance. So this is again returns the deviance value returned by the GLM function. Right, then few other things which are mainly for the descriptive purposes. For example, this table result which is for the outcome variable here, and then divided by the full number of observation, that will give us percentage success in training data. And then we have iteration. So as we talked about, the particular estimation technique that is used in logistic regression is different from multiple linear regression. We can look at more details, we can look at here. So we talked about that MLE is used typically used for logistic regression. However, you can see that, for example, we have been using GLM function, and within that we look for some of the arguments specifically for this purpose, the estimation technique purpose. We will get more detail. So we will see that GLM dot fit, we will see somewhere GLM dot fit method. So this we can see iteratively reweighted least square is used. The particular function that we are using, GLM, iteratively reweighted least square function is used, which is quite similar in approach with respect to MLE estimation technique that we talked about. MLM technique, MLM maximum likelihood method that we talked about in our discussion, as we can look in the slides as well. Maximum likelihood method, MLM method that we talked about. So this is quite similar to what the discussion that we have. So in particular R's implementation GLM function that we are using, it is the iteratively reweighted least square estimation technique that is used to estimate the coefficients that we have been doing. So quite similar to MLM, and as we talked about that number of iterations have to be performed to reach to estimate these parameters, so that we can get the best model, which is the best model which is fitting the data. So number of iterations actually indicate that, and then we have one metric which is quite similar to what we have multiple R square and linear regression, right. So this is actually computed using the deviance value. So null deviance and the standard deviation estimate or deviance that we have. You can look at the returned values here. So you can see deviance is the one of the returned value. So this is one, and then we also null deviance is also returned. So this is null deviance is with respect to the naive rule. So 1 minus this deviance divided by null deviance gives us a value which is quite similar to what we have in multiple linear regression, multiple R square. So this particular value will give us a metric which can be used to understand the goodness of fit for logistic regression model, and as on its own deviance also can be used. It is quite similar to what we have there in SSE, sum of squares error. So this is quite similar to deviance, is quite similar to that, and then we can have one metric, as I talked about, similar to multiple R square. So these metrics can be used to assess the fitness of model, goodness of fitness, goodness of fit of a logistic regression model. So let's compute some of these things. So residual degree of freedom, deviance, which is similar to SSE in linear regression. Then we have this proportions, percentage success in training data. Then we have number of iteration, and then we have a multiple R square kind of metric. Let's compute this. Let's create a data frame, and row names we have given some, and these are the values. So you can see residual DF is 87 here. So as you can see, let's again have a look. TF1 training partition, we have 96 observations, and if we go back to our summary results, right, if we go back to our summary results, we can see that how many variables we have here: 1 2 3 4 5 6 7 8 variables, and we can see that 87 is the residual DF. So 87 plus 7, that makes it 94, that is n minus 1. So that is the computation, that is how the degrees of freedom have been computed. So this is a correct value here. And then we have deviance value, which is also called as standard deviation estimate by some softwares, some statistical commercial statistical softwares. And then so this is all similar to what we have SSE, sum of squares error in multiple linear regression. Then we have number of iterations that have been used to arrive at the particular model that we have, that is mod 3 in this case. Then we have a value similar to multiple R square. So we can see 20% of the variability in the outcome variable has been explained by this model. So already talked about that this is being computed by 1 minus mod 3 deviance divided by null deviance. Now whether in terms of further in terms of deviance, the null deviance represents the naive rule value. So we have to see how much our model has been able to, how much reduction in deviance has been done by our model, and whether that is significant or not. So that can also be performed using this chi-square test that we can do. So we have one function p chi-square. So there we can actually use these two values. We can take a difference of null deviance and deviance. So that would be the reduction in deviance from a naive rule, and how much reduction that our model has done. And we can look at the number of predictors as degrees of freedom. Could be used, number of predictors that we have used could be used degrees of freedom, because these are the degrees of freedom that have been used to reduce the deviance, as we talked about, from 95 n minus 1 available degrees of freedom to we have reduced up to 87, that is residual degree of freedom. So 7 predictors have been used. That information can be used to perform chi-square test and to find out the significance of whether the reduction has been significant or not. So the third argument is lower tail, that is specified as false, and we can compute this chi-square value. So we can see that this is a small value, so therefore it seems that this reduction deviance is significant, which is also clear by the difference between the deviance and null deviance values. So we can also compute that. We can see this is null deviance. So let's look at the value, and we can have the deviance. Let's look at the value. So you can see, so the difference is so there is good enough reduction in deviance, and that is why it also came as significant difference. So these are some of the metrics that can actually be used to understand, to measure the goodness of it, to assess goodness of it for a model, as we talked about. I talked about that in a statistical setting. So these are some of the metrics which would be more useful. So in statistical modeling, we stop at when we build the model using the training partition. So typically all the observations are used that are present, and then we look assess the model with respect to some of these metrics. Now let's move forward to our next discussion point in logistic regression. So that is, let's move forward. So that is this particular point, whether linear regression can be used for a categorical outcome variable, right. So there are some situations where linear regression can be used as a categorical outcome variable, which we will discuss later. However, right now we are discussing some of the more important points with respect to overall general applicability of linear regression for a categorical outcome variable. So can be done technically, it can be applied. So we can treat the outcome variable as continuous. So the categorical outcome variable can be treated as continuous variable. So we can essentially do the numeric coding and keep it as a numeric variable, and technically we can apply, we will get the results. However, whether the results would be meaningful or not, that we need to understand. So technically it can be applied. We can treat the categorical outcome variable as continuous variable. We can code it numerically, so that can be done. However, there are going to be anomalies that would lead to spurious modeling. So what could be some of these things? So number one, predictions can take any value, not just dummy values. So for example, that binary logistic regression model that we have been performing on some of the data sets. So there our outcome variable, it typically has two classes, class 1 and class 0, and so the values, the dummy variable will take is 0 for class 1, 0 and 1 for class 1. However, when we apply a linear regression model to a categorical outcome variable, the prediction can take any values, any real value can be taken, and not just the dummy values 0 and 1. So that is one challenge. How do we map some of these predicted values, which can be any real value, to the actual values of the outcome variable 0 and 1. Now outcome variable or residuals don't follow normal distribution. So as we have discussed during a linear regression, that this is one of the important assumptions, that dependent variable, that is outcome variable or residuals should follow normal distribution, but that is not the case. As we can understand that categorical outcome variable will have just two values, 0 and 1. So it is actually follows a binomial distribution. So this particular assumption would also be violated. However, we talked about that because we are in a data mining modeling context. So where as we talked about, even if for prediction purposes, even if this particular assumption is violated, in terms of prediction it might not matter much, because generally we check performance on validation partition and test partitions. However, this case is different. The deviation from normal distribution is much higher. It's actually different distribution, binomial distribution. So that is one problem. Now the another assumption that we talked about in multiple linear regression is homoscedasticity. However, if we apply linear regression to a categorical outcome variable, this particular assumption would also be violated. the variance of outcome variable that we expect to be constant across all the records, that is the homoscedasticity property. So we to apply multiple linear regression, we want our outcome variable to follow this, to have this property. So variance should be constant across all time. However, if we look at the variance for our categorical outcome variable, it is going to be this particular value n times p into 1 minus p, and as you can see, because this is dependent on the value of p, so therefore the variance will change as the value of p changes. So when the value of probability value is actually close to 0, then the variance would be on the lower side, and when the value of p is approaches 1, then the variance would be on the higher side. So therefore the variance will not be constant, and it will increase as the probability value increases from 0 to 1. So these are some of the problems that we can see that we can directly understand, and why linear regression and cannot be applied to categorical outcome variable in a general sense, and the problems that we can see here. So what we'll do, we'll do an exercise in R to understand the same thing, to understand this particular aspect. So what we'll do, we will apply linear regression model on a logistic partition and see its applicability and see some of the anomalies or violations that could be there. So for this purpose, we are going to use, as you can see, multiple here. The comment is multiple linear regression model for a categorical response. So promotional offers is the data set that we are going to use for this particular exercise. So let's import the data set. Let's let it load. So once the observations have been loaded into environment, as we will see in the environment section, we'll do some of these steps. I think it has been loaded. Yes. So df2, we can see 5000 observation, 9 variables. So let's remove any columns or any rows if there are any. Let's look at the structure. So this is the data set. So we are already familiar with this. So let's go through some of the computations, some of the transformations that we have been doing in previous lectures as well. Let's take a backup. Let's get rid of let's select just these 4 variables, that is income, promotional offer, our outcome variable, then we have, I think, family size and online activity. So let's select them. So these are the variables selected for this particular exercise: income, promotional offer, family size, and online. So the variable that we are going to use for our outcome variable is going to be the promotional offer. As you can see that we have commented out the lines of code which we used earlier to convert these numeric variables into the categorical variables. So promotional offer and online, so they are actually categorical variable, factor variable, but we are not converting them into factor variable because we are going to apply linear regression modeling. So we'll keep them as numeric and we'll apply. So partitioning is the same, 60%, 40% in this case. So we can see that let's do partitioning. So df2 train, you can see 3000 observations, 4 variables. Now the same lm function is going to be used. Now the promotional offer is going to be regressed against all the predictors that are present in this particular data set, df2 train. So let's run this. Now what we'll do, we'll look at the summary table. So let's look at the results. So as we can see that income is intercept is significant, income is significant, and family size is significant. We can look at the different estimates. For example, income, quite a small value. Family size is also 0.03. Online is not significant. It has not been found to significant, as we can see. and we can have a look at the other values. We can see adjusted r square and multiple r square. So we can see if we 27% multiple r square value, we look at the p value, it's quite a small, so the model is significant. However, as we talked about, certain problems as we have discussed could be there, certain anomalies could be there. So what we'll do, we'll look at computing some of those things to check whether those anomalies are there in this particular case. So what we'll do, we are running ANOVA to extract some of the parameters here. So you can see, so sum of square errors, mean of square errors, and f value, f statistic, and the probability values for these the predicted income family size is given there in the ANOVA table. So what we are going to do is we are going to compute these particular values in a format that can be used for tabular presentation later on. So mod 4 sum, we have f statistics value, so that is returned as part of the summary function of model when we apply summary on the model object. So you can see this is nothing but f statistic value for the model, and then we have degree of freedom, and here, so we can see the degree of freedom, residuals degree of freedom, and the regression degree of freedom here. So that is going to be stored in this. So in this data frame, first we have the regression degree of freedom, then we have the residual degree of freedom, and then we have the total. So this data frame is about degree of freedom as is suggested by its name, df. Then we will compute sum of square error. So first we can see that in the ANOVA table, from the ANOVA table we are trying to extract out these values. So first sum of square for the regressors, regression, and then for the residuals, and then total. So this would be required in this particular variable ss, and then we look at the mean of square errors. So that is also being extracted from the ANOVA table results. You can see this particular column, mean square, and these values are being extracted. So first 3 values. So this head function, as you can see now, this role of this head function is quite different. In both these computations we have used head function. So you can see the second argument is -1. So what it actually does is it gives us all the values except the last value in the vector. So for example, mean square or sum of square, so there are 4 values in these 2 columns, in these 2 vectors. So except the last values, that is corresponding to residuals, the first 3 values are going to be returned. That means last value will be left out, and the remaining n minus 1 values are going to be returned. So that is what we want. So that will give us the corresponding sum of square errors or mean of square errors for the regression. So first that, then residuals. So let's compute this. Then let's also extract the f statistics from this particular vector that we have already seen. So let's do that. Then what we are trying to do, we are trying to compute the corresponding probability value. So probability value corresponding to the f test. So that is how it is being computed. Pf is the function that can be used. For more detail, you can go into the help section and find out more information about Pf. So you can see this is f distribution. So within f distribution we have a Pf function which can be used to compute the corresponding p value. So what we need is f statistics in the first argument, then we need degree of freedom as second argument, that is corresponding to a regression here, and the second is then last one is residuals degree of freedom, third argument, and then we have specified lower tail as false. So we will get the p value, corresponding p value. So let's record it in this format. Once this is done, we can create this table data frame, and let's assign names for this, and let's have a look at this particular table. So we can see that now once it's computed, So first column we have degrees of freedom. So for regression there are 3, and then because remember that we have used just 4 variables, one being outcome variable, so 3 predictors. So therefore degree of freedom is here is 3 for regression. Then for residuals it is the remaining, that is n minus 1 is 2999, total number of observation n is 3000, so residual degree of freedom 2996. Sum of square for regression and for residual is also there. So you can see that residual sum of square is much higher, so that also is we saw that the variance was also on the lower side, right? Earlier we saw that the variance that we had computed was on the lower side, so that is also indicated here. Mean square of errors is also there, and then we have epistatistic, and then we have p value, which is small value. So this gives us some information about the model. And now what we will do is we will use this model to score off a particular observation. So let us do a prediction for a new observation. Let us say this is our new observation is annual income of rupees 5 lakhs with 2 family members who is not active online. So this is information about a particular customer whether he is going to accept the promotional offer or not. So annual income is 5 lakh, family size is 2, and not active online. So we can use the predict function. First argument is as usual the model object mod4. Then in a data frame we are trying to pass on the values of predictors, for example income 5. So it should be in the same unit as was used for the modeling exercise in the training partition. So you can see 5, then family size is 2, and then online is because this particular customer is not active, so 0. So once we do this we will be able to predict this particular observation. So you can see this comes out to be a negative value. Now that was one of the first point that we discussed in the slide. Let us go back. You can see here that the predictions can take any value, not just dummy values. So we can see that a negative value has been taken here, and so that is in one anomaly that we can clearly see. And set of values for promotional offer that we already know, 0 and 1, and the value is that comes out to be predicted value comes out to be minus 0.14. now so one difficulty is how do we do our classification in this case. Now let us look at the residuals. So second anomaly that I discussed, that outcome variable or residuals don't follow normal distribution. So let us look at that. Let us plot a histogram and find out whether this is being followed. So you can see residuals, when we plot residuals, when we get histogram, you can see this is clearly not being followed, normal distribution is not being followed. One grouping here, another grouping where this is of lower values, lower frequency, and this higher frequency. So this is clearly looks binomial, different groups kind of thing. So definitely not following so normal distribution, and distortions due to real binomial distribution can be seen here. So the typically what exercises and the discussion that we have been doing was pertaining to classification task, and as we talked about that this is a statistical technique, logistic regression being a statistical technique is also applied used in statistical modeling. So the kind of tasks that we generally do in statistical modeling are quite similar to what we can call profiling tasks. So as we talked about in the starting lecture of logistic regression, that it's about understanding similarities and differences between two groups. So logistic regression can also be used to understand what are the variables which which can bring out some of the similarities or differences between groups. So let's discuss that aspect as well. So in profiling tasks, when we talk about profiling tasks, the situation is slightly different. So in the classification task, we typically build our model and look at the performance of that classifier, that particular model, using the classification matrix, using the overall accuracy or overall error matrix, and some deviations when we have a class of interest. So those are the things that we typically do. We also typically look at lift chart, especially when we have a class of interest, to in lift chart and decile chart, to see whether it's still despite higher error, whether still the model is useful in class of interest with respect to naive rule or average case. So some of those things that we do in classification task. However, in profiling task, what we do in classification, we follow that. So apart from model performance on validation partition, we also assess models fit to data on training partition, right? Because as I talked about, in a statistical technique, typically the whole sample is used. However, since we are using training partition for model building, so the models fit to data is assessed on training partition. However, model performance is assessed on validation partition for profiling task, and models fit to data is assessed on training partition. So some of these things we talked about when we talked about goodness of fit measures. We talked about the deviance, we talked about the 1 minus deviance divided by null deviance, that is equivalent of multiple R square. Some of those things you can see here as well. So models fit to data is assessed on training partition. However, we still focus on avoiding overfitting, because as we talked about, when we have metrics which look for, and when we do modeling to achieve the goodness of fit, then it can lead to overfitting. So still we would like to avoid overfitting and still be able to check the performance, still be able to have good classification performance as well. So usefulness of predictors is also examined in this particular case, profiling. So because it is about understanding similarities and differences between two groups, so therefore which predictor is more helpful in terms of bringing out those differences, those similarities. So when we build our model, we also look at the significance levels of some of these predictors. We look at which predictors are significant, which are not significant, whether the not significant predictors can be dropped from the model. And this has also should be looked at from the perspective of model performance, because as we have talked about data mining model, we would like to keep the insignificant variables also in the model if they provide some practical importance in terms of scoring new observations. However, in classical statistical modeling, we just drop the insignificant variables, because we are just interested in understanding the phenomena, understanding the underlying relationship. So profiling is quite similar to that approach. However, because we are doing data mining modeling, so we have to balance between these two. We have to balance between performance and also the main profiling task. So we have to really see whether the predictors can be dropped just like in the statistical setting, or whether they have to be kept in the model, because they also provide some practical significance for scoring new observations. So that balance has to be achieved. So we have to avoid overfitting, we have to look for usefulness of predictors in both the context, data mining context, prediction point of view, and also statistical context in terms of understanding understanding variables which differentiate the groups, which bring out similarities or differences between groups. So this kind of exercise is done in profiling task, and goodness of fit matrix that through an exercise in R that we have already understood. So we look to understand first, we look to understand the overall fit of the model. So if the overall fit of the model is good, only then we go ahead and look at the individual variables. So first step typically is in profiling or in statistical modeling, we look at the overall fit of the model. So in this particular case, logistic regression, as we talked about, the deviance is the metric as we talked about in previous lecture that could be used, and we also said that this is equivalent to SSE in linear regression, and 1 minus deviance divided by null deviance, that is equivalent to multiple R square in linear regression. So these are two metrics that could be used to assess the overall fit of the model. And then once this is done, then we look at the single predictors, we look at whether they are significant or not, as I talked about, and whether we can strike a balance in terms of prediction performance, classification performance versus the profiling, that is and also statistical modeling context. So, with this we move to our next discussion, that is about so till now the exercises that we have been doing, they were mainly focused on binary classification, binary logistic regression model. We just had two classes, class 0 and class 1. Can logistic regression be extended to a scenario where we are dealing with more than two classes, where we are dealing with m classes? So, yes, it is possible. So, we will discuss some of those things. So, first one is multinomial logistic regression. So, multinomial logistic regression. So, the categories, the classes that we have, they are so the categorical variable is nominal. So in that case we can apply multinomial logistic regression. So, what happens in multinomial logistic regression, first out of those m classes that we have to select one, we have to pick one as the reference category, and for the remaining m minus 1 classes we create separate binary logistic regression model. So, for each of the m minus 1 classes apart from the reference category class, so we will have m minus 1 classes. So, for each of the m minus 1 classes we will create separate binary logistic regression model. That means, for a class 1 we will have the scenario where the observation probability of belonging to class 1 and probability of not belonging to class 1. So, that kind of binary scenario we will have, and that for each of the m minus 1 classes. So, we will be dealing with m minus 1 binary logistic regression equations, and so using that we can compute all those probabilities values with the help of the predictors, and then the remaining reference class, that probability for that can always be computed by the m minus 1 probabilities values for the m minus 1 classes. So, we can just subtract that from 1 and then we can get for the probability value for the reference class. And once we have the probabilities values for all m classes, then we can apply our most probable class method routine, where the class having highest probability value would be assigned to the new observation. So, this is how we can go about applying logistic regression to an outcome variable with m classes. So, this is a multinomial logistic regression, and this is applicable mainly to nominal variable, right. So, the categorical variable having nominal classes. The second scenario is about when we have a categorical variable with ordinal classes, we have a ordinal variable. So, in those cases we can apply ordinal logistic regression. So, again within this ordinal logistic regression we can have two scenarios. So, as we have understood in some of the initial lectures and supplementary lectures, that ordinal variables they have order among different labels is also important, that is also meaningful. So, less than or equal to or greater than or equal to operations, they are also applicable in this case. So, the first scenario is large number of ordinal classes. So, if our outcome variable, which is categorical variable with ordinal classes, if that variable is having large number of ordinal classes, then one solution is treat that ordinal variable as continuous variable and apply multiple linear regression, right. So, when we have a categorical variable with ordinal classes, so we have a categorical outcome variable, with m ordinal classes and m is large, then as I talked about, we can treat this particular variable as a continuous variable and apply multiple linear regression. So, multiple linear regression can be applied, and reason is one justification for this is, as we talked about earlier, that in the binary situation we have just two values for a categorical variable, and the predicted values using MLR can range anywhere, any real value. So that was the one main problem here. But when we have m is large, that means set of values could be many more. So it could be, if there are 50 groups, let's say, so in this fashion we can go on up till this. So the number of values that can be taken by this particular ordinal variable are many more. So therefore the predicted values, this can be easily mapped to some of these values, could be close to some of these values, and probably multiple linear regression can be still applied. So this is one way. When we have an ordinal variable with many number of classes, large number of classes, when m is large, then still instead of logistic regression we can apply multiple linear regression. So that is first scenario. The second one is, what if we have a small number of ordinal classes? So if m is, in this case, m ordinal classes that we have, if this is small, m is small, then probably we will run into the same problem like for binary classification. The similar problem would be there. We will have only few values, 0, 1, 2, 3, let's say these many. So again, small number of classes, small number of ordinal classes, so we'll have will run into same problem. So what we do is we use a different version of logistic regression called proportional odds or cumulative logic method, as indicated in the slide. So small number of ordinal classes, so we would like to use proportional odds or cumulative logic method. So what we do here in this particular method is we create separate binary logistic regression model for m-1 cumulative probabilities. So we talked about that when we discussed multinomial logistic regression. So for all m-1 classes we'll have separate binary logistic regression model. However, if you see that here we'll have separate binary logistic regression model not for m-1 classes, not for presence of that class or absence of that class, but m-1 cumulative probabilities. So let's understand what we mean by that. So let's take an example for a 3-class case, as written in slide. For a 3-class case, C1, C2 and C3. So let's say these are the 3 classes, ordinal classes C1, C2, C3, and a single predictor x1 that is being used. So our logit equations could be something like this. Logit for C1, it could be alpha 0 plus beta 1 x1, and logit for C1 or C2. So that means from C1, first logit equation is just for an observation belonging to C1, the second is observation belonging to C1 or C2. So that gives us the cumulative sense. So as we talked about that ordinal, the order is important, so that means different classes can be compared. So therefore C1 or C2 is a meaningful here in the sense that if we look at the right part of the equation, beta 0 plus beta 1 x1, you can see that beta 1 is same in both these equation x1. So you can see, because this is the comparison can be done. So the coefficient, so the intercept are only difference because the comparison. So one is when we talk about ordinal, so one particular class, this ordering is this is meaningful. So when the ordering of classes is meaningful, that means one can be said less than one particular class or higher than one particular class, just like the categories that we might have: high, low, medium, upper, medium, and then low. So this kind of classes we might have, or we might have strongly agree to, strongly disagree. So those kind of ordinal classes where the order is meaningful, then in those situations we can have something like this cumulative probabilities values, and beta coefficient can be used. The same beta coefficient can be used for both these logistic equation, and from this we can compute the cumulative probabilities values. And once these cumulative probabilities values for two of the classes for these classes have been computed, the actual probabilities values for C1, C2, C3 can be derived from using the probability value that formulation that we have. So from logit we can derive the probabilities values. So once these cumulative, from there, once we have the probabilities values for all these classes, then we can again apply the most probable class method, and also assign the class based on the probability value. And again this in this fashion we can apply ordinary logistic regression to a scenario with fewer number of ordinal classes. So what we will do, we will go through OR Studio and do an exercise for this when we have classes more than m is greater than 2. So logistic regression modeling for classes greater than 2. So what we will do, we will create a hypothetical data set here. So number of observations are 1000 in this case. So as you can see, n is 1000. So let's create this. Now what we are going to do is, we are going to create a data frame, a hypothetical data frame where we have two variables x1 and x2. X1, as you can see, we are using run if for x1 and x2 both. So the observations, so the values will lie between 0 and 100, and n number of values would be created, that is 1000 values would be created lying between 0 and 100. So let's create this data frame. Let's look at some of the observations. First 6 observations, you can see all the values, they are lying for both the variables x1 and x2, they are between 0 and 100. Now what we will do, we will create a categorical outcome variable with 3 classes. So this particular data set that we are trying to create, we are going to use it for both the scenarios, multinomial scenario and ordinal scenario, right. So this is just for illustration purpose. So we are not specifying whether the variable is ordinal or not. So we are just going to use it for both the scenarios. So what we are going to do is, we are using transform function to create our outcome variable, categorical outcome variable. So you can see that we are trying to compute y as 1 plus if else, and if the value is less than 0, this particular value 100 minus x1 minus x2, plus again a certain value is being taken from normal distribution, standard deviation 10, 1000 values. So if it is less than 0, then using this information, that is information based on x1 and x2 and certain additional computation, we are trying to assign it a class 0, or then the second, if that is not true, then second computation, so it will get a class 1 or class 2. So let's compute this. Once this is done, let's look at the observation. So you can see another variable y, that is categorical variable, has been created, having you can see 1 and 3, 2 values are being taken. Let's look at the structure of this particular data frame. So these are 3 variables, x1, x2 values between 0 and 100, and y is taking value 3 values 1, 2 and 3. So let's plot this particular data set. So this is our default palette. So however, I would like to use this palette, gray, 3 sets. So in this fashion we can have sets of number of sets that we require. So let's look at the range of x1, y and x2, which is already, because we have just now created these variables, so that is actually clearly understood as well. So limits 0 to 100, 0 to 100, and then coloring is with using this particular factor y So you can see as dot factor we are using this particular variable, and let's create this plot. So you can see, so this is our plotting. So one group is here, the second group is having some medium level gray shade here, and the third group is here, which is lighter gray color. So these are the values that we are going to use, x1, x2. So this is plot between x1 and x2, and the outcome variable has been color coded. So 3 categories. Now what we will do is we will use the multinomial logistic regression. So for this we need this package, library NNet package. This package is actually for neural network, but it provides us offers us this function which can be used for multinomial logistic regression. So multinorm is the function. So what we are going to do is the outcome variable y, we are going to regress it with the remaining variables, that is predictors in this particular data. So all the observations we are going to use here. So let's run this. Let's look at the summary. So we can see coefficients x1 and x2, right. We can also see the error values, residual deviance, and AIC values are also indicated here. Now fitted values also we can look at first 6 observation here. So we will get these fitted values which are nothing but estimated probabilities values for these 3 classes 1, 2 and 3. So this is what we have. Now if we had another partition validation or test partition, we can use predict function to score those partitions and have probabilities values, estimated probability values for those new observations. However, for demonstration purpose, we are applying predict function on the training partition, that is the full data set itself. So you can see another argument that we can see is type, which is props, which is for probabilities values. So let's run this, and you would see we'll have the same probabilities values which were fitted. So we can see here that same values, you can see first row it is same values. So the fitted values now we have got the same one using predict function. Now let's classify these observations. So this is how we can classify. If the probability value for 1 is greater than the probability value for class 2 and also greater than the probability value for class 3, then of course this observation has to be classified to class 1. Otherwise we will again compare the probability value for class 2 with probability value for class 3. If again it is greater than class 3 probability value, then the class 2 is assigned, otherwise class 3. So in this fashion we can assign all the observation into appropriate classes. So this is implementation of most probable class method. So once this is done, you can see mod train C for all 1000 variables have been created, and observations have been assigned to appropriate classes. Now let's look at the classification matrix. So we can see actual value, predicted values. Now till now the classification matrices that we have been observing, that we have been creating, they had 2 values 0 and 1, and we had 2 by 2 classification matrix. Now this time we are seeing 3 by 3 classification matrix. So 3 possibilities for actual values 1, 2 and 3, and the predicted values, and we have the corresponding numbers here. So you can see that again the diagonal element, that means these 3 elements, they represent the values records which have been correctly classified, and the remaining observation of diagonal elements they have the records, they have the counts of record which have been incorrectly classified, right. So from this we can compute the classification accuracy, that is 91% in this case, and error, that is the remaining 9%. So in this fashion we can apply multinomial logistic regression to a particular data set. Now let's move to next part, that is ordinal logistic regression. So in this particular case, ordinal logistic regression, as I talked about, 2 scenarios. So one where m is large. So in that scenario we can apply multiple linear regression. One exercise that we had done in previous lecture, we had applied multiple linear regression, but that was for the class which had just two for a variable, categorical variable which just had two classes 0 and 1. In the same fashion, for the first scenario, the multiple linear regression can be applied. So there is not much difference in terms of applicability. So what we'll do an exercise for this scenario where we have to apply this ordinal logistic regression, the cumulative probabilities method, cumulative logit method. So for this we need this package mass. So let's load this particular library, and we have POLR is the function for this. So this is actually for probit. However, it can also be used for the cumulative logit method. So we'll just see in the help section. So you can see POLR, this is ordered logistic or probit regression, right? So what we are interested in ordered logistic regression. So so here ordered logistic regression, you can see in the method argument, the first one is logistic. This is actually ordered logistic method. This is also called proportional odds logistic regression, which we have discussed, right? So let's go and build this model. So POLR is the function. So first, as you can see, y variable I have converted into a factor variable, and then regressed against all other variables that which are predictors. Data is full. Then we need this argument as well, has, which is mainly if we want to apply for summary function later on the model object. So this is also true. So now let's apply summary. So we'll get the results. You can see the coefficient values here, x1 and x2, the value and the error and the t values are also there, and we have the residual deviance and AIC value as well for this particular model. And if we are interested in finding the fitted values, so that is also returned by the model. So let's look at some of these values. You can see for each of these classes, class 1, 2 and 3. So these values are actually probability estimated probabilities values. Now using these values, we can again apply the most probable class method. So first we need to compute the do the assignment as per the most probable class method, like we did in previous exercise. So as I talked about, predict function can again be used to score new data. So in this case, we are scoring the training partition itself again. So we expect to get the same values. As you can see, last row, you can see here also the same values are there. So it is the scoring of the training partition itself. So we'll get the same observation. Now what we'll do, classify observations. So as we did in previous exercise, mod 1 train for class 1, probability value for class 1 greater than probability value for class 2 and greater than class 3, then assign it to class 1. Otherwise again we will do one more comparison. The probability value for class 2 is greater than probability value for class 3, then assign it to class 2, otherwise class 3. So in this way we will have the appropriate classification scores. Now let's generate the classification matrix here. So you can see 3 by 3 matrix. We have 3 classes, actual values, 3 possibilities, predictor values, 3 predicted classes. So again, diagonal elements, they represent the correct classification values, and off diagonal elements, they represent the incorrect classifications. So what we can do is, let's compute a classification accuracy, and we can see 82%, and the remaining is error. So with this we have completed our discussion on logistic regression. And so today we have been also able to cover the scenarios where more than 2 classes are present in our categorical variable, what happens when the classes are nominal, and how we can apply logistic regression when classes are ordinal. So we have seen that. We have also done an exercise in R. So we stop here, and we'll continue our discussions in next lecture for a new technique. Thank you.